So hello everybody, my name is indeed Hannes Marijn from Ghent University and imec in Belgium. And this work was also done in collaboration with the Northumbria University in the UK. So the work is about video watermarking, but rather than going immediately into this long and complicated title, this work is actually about Pirates of the Caribbean. And more specifically about how to distribute videos such as Pirates of the Caribbean safely. And this is, of course, to have the fight against piracy. So when we want to distribute videos, for example, as a streaming service to only the users that are paying for this service, we can simply send this video to all of them. Let's say to Will, Elizabeth, and Jack, and they are the only ones that should be able to watch this video. Well, we don't want then that this video ends up on the Pirate Bay so that all of the peasants who are not paying for it can also watch the video. So if this video is leaked on the Pirate Bay, we do want to know who is this pirate that leaked it. Is it Will, Elizabeth, or Jack? So that's why we do forensic watermarking. We can embed a watermark, for example, the text here in the lower left corner, where we see the receiver ID and the name of the receiver, so that if somebody leaks the watermark, we know who it is. For example, Will gets the watermark number 1, Elizabeth number 2, and Jack number 3. And then we find a video on the Pirate Bay. We can simply read out the watermark.
Oh, well. Jack Sparrow. Captain Jack Sparrow.
So by reading out the watermark, we know that number 3 here is Jack Sparrow. Oh, I'm sorry, Captain Jack Sparrow.
You are without doubt the worst pirate I've ever heard of. But you have heard of me.
So a pirate would be a very bad pirate if he didn't do anything about this obvious watermark in the lower left corner. So he can do an attack on the watermark, for example, by hiding it with a box or blurring it or something like that.
Gentlemen, milady, you will always remember this as the day that you almost caught Captain Jack Sparrow.
So, they can do an attack on the watermark so that they're not identifiable anymore. And you might think that this obvious watermarking technique with text in the lower left corner, it isn't used in practice. But actually here we see the introduction of a Game of Thrones video that I found on the Pirate Bay. And in the lower left corner, we can in fact see a blurred watermark. So there was some text stating some ID, such as number 3 Jack Sparrow, and the person just blurred this watermark before leaking it on the Pirate Bay. So now let's take a look at what are some requirements for better forensic watermarking techniques, better than the textual watermarking technique. So first of all, the watermark should be invisible. We shouldn't even know that it is there. And this also means that the watermark should not decrease the video quality. We don't suddenly want to have a lower quality just because we add some security. Also, it shouldn't increase the video file size. For example, Netflix, the streaming service, accounts for more than 10% of the global internet traffic. If they would suddenly increase all of their video file sizes, this would have a huge impact on the global internet consumption. Also, the watermark should be robust, meaning that it should survive attacks by pirates. So, for example, we shouldn't just be able to blur out the watermark so that it's not readable anymore. So, actually, these two requirements I already fixed in a previous work called Rate-Distortion-Preserving Watermarking. And I will quickly recap what I did in that work. There we did watermarking by doing a slightly different compression. And what does this mean? So if we have an uncompressed video, we can simply compress that. And these videos kind of look the same, although, as we all know, when we do lossy video compression, there are actually a bunch of small compression artifacts in there. But if we set a high enough quality, we don't even see these compression artifacts as humans. Now, for the watermarking, we simply do this compression slightly differently. We make some few subtle changes during the compression process, creating a slightly differently compressed video with a bunch of different compression artifacts again. And the thing is that these compression artifacts are not the same. So the differences in compression artifacts, the differences in invisible compression artifacts are the watermark. And most importantly, here we see a compressed video, and here we see another compressed video with the same bit rate, and the videos look the same, but they actually aren't. They differ in some compression artifacts, and that is what is used in this rate distortion preserving method. So this watermark is in fact invisible. But so now what happens if we do an attack on the watermark and we do a recompression to a lower quality, trying to hide all of these invisible compression artifacts that we use as a watermark representation? So how do we do the detection of these type of watermarks? So when we have a pirated video in the bottom left here, we can simply compare this to all of the watermarked videos that we know that we have distributed. And we can simply do this on a pixel by pixel basis, comparing this video to all of the watermarked videos. And we can plot the distances in a graph. And we see that one of those watermarks is more similar to the pirated video than all of the others. And that's how we know that watermark number 10, in this case, is in fact the watermark that is present in this pirated video. So the watermark is robust doing this detection. But there are some problems with this, and that is what I'm trying to solve in this proposed work. So the first one is that we have to do this pixel by pixel comparison of these raw videos, and that takes a lot of time. So in fact, the watermark detection, it should be fast, but it is not. Secondly, when we do this detection, we need access to all of these watermarked videos. And that is kind of a security leak in itself. So having to have access to the original video or of all of the watermarked videos, that is not something that we desire. So we want the watermark methods to be blind, but in fact, this existing work is not blind yet. And that is where the proposed method comes in. We want to do a fast and blind detection of these rate distortion preserving video watermarks. So how do we do this? Well, we do this using hashes. So instead of comparing the raw videos to each other, we first create a hash of each of these watermarked videos. And we also create a hash of the pirated video. And the difference is that these very large raw videos are now converted into very small hashes. And then we don't need these large videos anymore. So we can do it in a blind way. And then we can simply compare the pirated hash to all of the watermarked hashes. And because these hashes are so small, this can be done very quickly. And similarly, we can plot the distances of the hashes on a graph, and we see that number 10 here is a detected watermark. So we can do it robustly, let's say. So how does this hashing work? Well, without going into too many details, because time is limited, I will quickly give you an overview of this. So when we have a video, we can do some pre-processing first to downsample it in time and space to already reuse the file size of the video, let's say. Then we divide this video in blocks. For each block, we calculate the luminance block mean, and then we calculate the differences of these means in the three directions that we can traverse the video. So in a temporal way, a vertical, and a horizontal spatial way. Then we get three signals, three 3D signals, and we want to convert these into three 2D signals. And we do this using some kind of signal calibration, using the normalizing shift, the DCT, and the DST. So without going into too many details, those can be found in the paper. We can make this signal less and less large. We can then do a binarization step that each 8-bit integer is converted into a single bit, and we can concatenate these and we get the hash. And so the most important thing is that this very large video is converted into a very small hash. So before here, I show this in a blind way. We simply need a video and we can create a hash from it. But we can also do this in a non-blind way. And that is if we have access to the original video, we can subtract this, or after the pre-processing, from the video to create a hash then. And the advantage of this is, like shown in the image here, if we do it in the blind way, we are doing it from the content of the video that includes the watermark. But if we first subtract the original from the video, then we only get the bottom picture here, which is only the compression artifacts. So we are not hashing the content anymore, but only the compression artifacts, while in the blind way, we're hashing both the content and the compression artifacts, which of course is less efficient. So that's why we propose to have both options. So now on to some results. How robust is it? So how robust is this fast detection method? Well, first we need to have a baseline of the slow detection method. So as I stated before, in the slow detection method, we need to compare the raw videos. For example, for a 10-second 1080p video segment, we need to compare 1 to 2 gigabytes per video. And here I will quickly go over how this table of robustness results works. So when the watermarked quality is very high, we have a few compression artifacts that represent the watermark. And then we can do a recompression in red, the attack, to another quality level. For example, also a very high quality level. And then we get a 0% false negative rate, green, which means that we can always detect the watermark. But if we make the attack stronger, to, for example, an extremely low recompression attack, then the watermark is not always detectable anymore. So we get a false negative rate, in this case of 87%. It's red, which means that we can't always detect it anymore. But now if we have a worse watermarked quality, which means that we have more compression artifacts that we use as a watermark representation, the watermark actually becomes more robust. So we can go worse and worse, and we see more green, which means that it is more robust. So this is the state of the art. This is the rate distortion preserving method using the slow detection. And we see that in the top right corner, we have the non-green values, and those are the places where the watermarking method is not robust. And as an example here, we have a watermark quality high and then an attack quality very low, and we get a video like this. And I hope that through Zoom, this is also shared nicely, that you see a bunch of compression artifacts. The quality is not very high anymore, but yet still we can detect the watermark using this method. But so now, most importantly, we want to compare the slow detection method to the fast detection method. So in the slow detection method, we needed 1 to 2 gigabyte per video segment. Now we can do it with 5 kilobyte per video segment. And we do this first in a non-blind way. And if I go back and forth here, you see that suddenly the top right corner of this table, there are more values in red. So it's slightly less robust, but still there are a bunch of values in green, which means that it's robust in those cases. As long as we don't significantly decrease the attacked quality, we can detect the watermark. And we can go even more extreme and go to 0.5 kilobytes per video segment. And then again, more values become orange and red, which means that it is less robust. But still, as long as we don't reduce the quality during the attack significantly, we can detect the watermark. So now, before we did this in a non-blind way, what about blind detection? So where we do not have access to the original video and where we do not subtract it first before we do the hashing. So in this case, we use the 40 kilobyte hash, which is a bit larger, but still we see that as long as we don't significantly decrease the quality of the video during the attack, we can detect the watermark. And for example, here, when we have a low watermark quality and a very low attack quality, we get a video like this. We can barely see the faces. It's a very low quality, but we can still detect the watermark with a 0% false negative rate. So how fast is it? Well, it is very fast. In the experiments that we conducted, it was up to 5,700 times faster to do this comparison using hashes rather than using full raw videos. We also know that blindness is possible in this method, as I proposed, and the watermark is still waterproof. There is a modest decrease in robustness, depending on if we want to do it blindly or if we want to have very small hashes, but still the watermarking method is robust, as long as we don't significantly decrease the attacked quality. So in conclusion, we get a watermarking method that is invisible, robust, fast, and blind. And that is how we get to the fast and blind detection of rate distortion preserving video watermarks. So in conclusion, pirates, you should beware because, with this new method, we can come and get you. So my name was Hannes Mareen from Ghent University and imec. I'm happy to answer any questions you may have. You can also send them by email or send me a LinkedIn invite, and I'm happy to answer anything. Thank you.